Okay, students, we learn in this class Newton's third law of motion in physics. So again, it is useful or required class students, intermediate students, NEET appearing students, and JEE appearing students. Not only that, engineering students also it is required. Coming to that. Newton's first law and second law. Newton's first law and second law deals the effect of force when acting on a body. The first law states that unbalanced force produces a change in the velocity of a body. The second law states that the force needed, the amount of force needed produce a given acceleration. Okay, so these are the statements. First law states that if there is unbalanced force, the object get acceleration. Unbalanced force, this is the, let us assume this object, suppose it is in the rest condition. If you apply a force, this object get into this is unbalanced force. This object get into the velocity. Suppose if there is no force, it is keep on in rest condition. That is the unbalanced force. Means of course if you apply a force in F1 force in this direction, F2 force, and obviously F1 greater than F2, obviously the object is get acceleration in this F1 direction because F1 force is greater than F2. So that is the statement. So for first law. The second law states that the force is needed to produce a change in a given acceleration. So that means suppose this object is there. Suppose this object get accelerated 2 meter per second square. We have to calculate the force. What is the force? What is the amount of the force that is required to act on this body? Then only this much of acceleration is obtained by that object. Of course, this object has mass. So this is the statement of this second law. Okay, coming to that third law. When two bodies interact with each other, Newton's third law states that in any interaction between two bodies, the force applied by the first body on the second is equal and opposite to the force applied by the second body on the first. So that is the statement. I hope you can understand that. Simply we can say that action equal to reaction. Of course, that simple statement is not enough. The first force applied by the force applied by the first body on the second is equal and opposite to the force applied by the second body on the first. That is the Newton's third law. Okay, we can take 2 examples to understand Newton's third law. Action and reaction are always equal and opposite. Action and reaction, they are opposite and equal. For example, if you take this one, this is the block. That block is acting. That block is exact force on the table. Let us say that is a action because of this block exact force on the table. That is the action. The reaction is given by that table in this direction, so that block is in the equilibrium condition. That is in the stationary condition. So therefore, the stationary conditions means that block is exerting force on the table. That is action. The reaction, the same quantity of force is exerted by this table in the opposite direction. That is the reaction. Another case, this is also you can take here, action equal to reaction. In this case also you can take this is the block, this is the block, okay. This is the hand. The hand is putting here to stop this block, so that this block is exerting force on the hand. The same quantity of force is exerted by this hand in the opposite direction. Opposite direction. F1 is exerted by the hand. F2 is exerted by the block on the hand. So therefore, this is also satisfying the Newton's third law. Opposite and equal. Opposite and equal. Equal. So here we can understand that in the another example, F1 equal to F2. Another example, you can take a porter. He take the luggage on his head. Obviously that luggage is exerting pressure on the head. That is the action. The head is the head is exerted the reaction in the opposite direction, same quantity on the block, so that is it is in the condition, in this condition, that is equal to F1 equal to F2. So what we can understand here, the action and reaction are the two opposite forces that act on the two different bodies, that act on the two different bodies. This is the block is exerted the head, this is the action, the reaction exerted by the head on the block. So they are in the opposite and equal, that is the meaning. Coming to this case, the any pair of equal and opposite forces is not an action-reaction pair. Please understand that. And any pair of equal and opposite forces is not an action and reaction pair. That means any equal and opposite forces not satisfy the Newton's third law. Not satisfy the Newton's third law. How it is not satisfy the Newton's third law? We can understand from this diagram. You take it. This is the table. On the table I put a book. Let us say that this is the book. Obviously that book is because of there are number of pages. Once the book is put on the table, that may be the pages are let up and get disturbed. But that is in the stationary means that weight put on that table. That table is exerted on the force in the opposite direction of the book. That is let us say normal force, that is called N. But whereas that book weight is acting in the downward direction because of earth. The earth is pulling that book in the downward direction. So therefore normal force, the force exerted by the table and the book weight is acting in the downward direction, pulling by the earth. These pair of forces are not considered as a Newton's third law, because that book weight is pulling by the earth. Please understand that, earth. Whereas the book force that is exerted by the table. So N is the reaction, normal reaction by the table, whereas the book weight is due to the earth. So therefore these kind of forces is not considered as a Newton third law. Obviously that forces are the two opposite forces acting on the two different bodies. Means this is the object is here, earth is pulling, so there is no connection. Of course it is pulling by the that weight is because of earth, but earth book there is no connection, but the connection between the table and the book. So therefore the third law is not satisfied in this condition. Of course they are equal and opposite force. N equal to W, but this third law is not satisfied in this condition, because the book table is exerted force on the book because of book, but the book weight is due to the book is pulling by the earth. So the connection is not taken into the consideration of the book and the table. The connection between the table and the gravitational force of the earth, there is no connection. That we have to understand. Okay students, coming to that another concept, Conservation of linear momentum. Conservation of linear momentum. Conservation means matter neither created nor destroyed, or the energy from transformed to one form to another form, but it is not destroyed. It is not destroyed. In the same way, if you see this statement of definition of this conservation of linear momentum, if net actional force on a system of particles is zero, the linear momentum of the system remains constant. The linear momentum of the system remains constant, which means that net force, the actional force is zero, the net actional force is zero, the linear momentum of the system remains constant, which means that this is the one object is here, another object here, let us say that A, let us say that B. This is that there is no actional force. This is the mass equal, let us say that m1, this mass equal to B object mass m2, m1 velocity equal to u1, the m2 velocity is equal to u2. This is the moving in this direction, this is the moving in the opposite in this direction. Also, the linear momentum of the system remains constant. Linear momentum of the system remains constant. What we can understand, how we can understand this that statement, they are moving in this direction, but at one instant they get collide. So both are they collide in this at this instant. So what is happening here? Before collision, what is the momentum of these two objects A and B? You see that mass into velocity gives the momentum of this object. So let us say that let us assume that is the 80 kg meter per second. B momentum before collision, that momentum V u2 into m2, let us say that is equal to 240 kg meter per second. After collision, this total momentum equal to 320 kg meter per second. 320 kg meter per second. After collision also that the momentum remains constant. You see that from here we can understand, after collision A get 100 kg meter per second, B get to 220 kg meter per second. If you sum these, add these two things, again you get the 320 kg meter per second. But thing is that we can understand here the momentum of before collision A momentum 80, after collision A momentum 100, before collision B momentum 240, after collision B momentum 220. So after collision B momentum is reduced, that is go to the A. After collision B to A. So that equation is balanced, the momentum is balanced, but that's why the momentum is conserved. It is not go to anywhere. It doesn't go. It did not go anywhere. It is there. Before collision the momentum is equal to 320. After collision, but momentum may be exchanged by one body to another body, but it remains constant. It is remains same. This is the meaning of this statement. That is the meaning of this statement. Of course, by taking this simple numerical values we can understand, but we can derive the equation. Okay, students, now we derive that law of conservation of momentum equation. Okay, students. So now you can see here. So this is the object m1, this is object A, this is the object B. The M object mass equal to m1, B object mass m2. Without any external forces, the object is moving in this direction with u1 velocity. The B is moving in this direction u2 velocity. V2 velocity. After they are moving together in opposite direction. At one instant, obviously they get collide. So therefore, what is happening here? Once they are collide, the B object exert force on the A. So therefore, this is the force. Let us say that this is the F1. A object body is exert force on the B, that is acting in this direction. But one thing we have to understand here, during the collision, the contact is taking place between these two objects. During that contact, the time is required. During that contact, the time is consumed. That short time is consumed. Let us say that is t. That is time t. So during that collision, collision, the short time is taking place, the time t, then only the force is get into the picture. Then only the force into get into the picture. So therefore, once the collision is over, obviously this because of this force B exerted A on the force F1, obviously this object is moving in this direction. The A force exerted on the B because of this object is moving in this direction. But the moment the final velocity is let us say that V1, this object velocity is U2. Of course, the velocities are relatively changed. Of course, this object get more velocity, this object get more velocity than before collision. This object get this A object may get more velocity, final velocity before collision. B object may get less velocity before collision. But the velocities are changed. So therefore, this force, let us say that this force is F1, this force is let us to F2. So therefore here I would take the sign convention here. F1 is taking a minus, F2 is taking F2 is taking positive. F1 equal to F2. So their force equal to 0. Then only the relative momentum remains constant. The linear momentum remains constant. They are not changed before collision and after collision. After collision already we have seen in the previous in the just before with the numerical examples. Numerical examples. Okay, you coming here. So I would take a sign convention from left to right positive, right to left to negative. So that's why I have given the negative sign to F1 force. F2 is positive. You coming here, minus F1 equal to F2. The force equal to, I would like to write rate of change of momentum. That is equal to M1 V1 minus M1 V1 equal to M2 V2 minus M2 U2 divided by time t. That is a minus. So this time is nothing but t during the collision, that is the taking place during the collision, that is the time is consumed. That time is consumed by the two objects. So therefore the time. So this is also time. So both are same. They get cancelled. So that this equation can be rewrite like this: minus M1 V1 plus M1 U1 equal to M2 V2 minus M2 U2. If I rearranged that equation, M1 U1, this will take this side, plus M2 U2 equal to M1 V1 plus M2 V2. You can understand here. Now the momentum before collision equal to the momentum after collision. This is the satisfied. The equation is satisfied. This is the before collision. This is the after collision. The momentum is the before collision, M1 U1 plus M2 U2. After collision, M1 into V1 plus M2 into V2. So the condition is the law is satisfied. After collision, so what is the law? States that the total momentum before collision equal to the total momentum after collision. So momentum does not go anywhere. That momentum remains there, but they may be changed from some relatively the momentum from one body to another body. But before momentum equal to after momentum. So this way we can derive that law of conservation momentum equation.